In this section, we are going to solve a few questions based on similarity. It is given that in this particular figure, these two angles are equal to 46 degrees, and the measurements are given. LM is equal to A, PN is equal to X, MN is equal to B, and NK is equal to C. We have to prove that X is equal to A into C divided by B plus C. So this is what we have to prove in this particular question. Now if I were to look at these two angles, each of them is 46 degrees, and this tells us that because these angles are equal to each other, I can say that PN is parallel to LM because the corresponding angles are equal. So I can say that angle PNK is equal to angle LMN is equal to 46 degrees because this is given to us. And because these are corresponding angles and they are equal, I can say that this implies LM is parallel to PN. The reason is corresponding angles are equal. Corresponding angles equal. And now because these two lines are parallel to each other, I can definitely think of similarity. The reason why I am picking similarity for this particular proof is X and A form the sides of two different triangles, and here I have C as the side of triangle PNK, and B plus C will be the entire length of MK. So that's why I am considering similarity between these two triangles, because that will help us identify a relation between X, A, B and C. So let us now take these two triangles for similarity. So I would say consider triangle PNK and triangle LMK for similarity. So let us draw these two triangles separately now so that we can understand more about these triangles. So I have drawn these two triangles separately over here. You will notice that 46 degree and 46 degree, these two angles are equal to each other. So I can say angle PNK is equal to angle LMK. That's given to me in the question. It's given that both angles are equal to 46, and angle PKM is equal to angle LKM because these are again common angles, right? And therefore I can say that triangle PNK is therefore similar to triangle LMK, again because of the AA test. I can apply AA test here because K is the common angle, and not because it is the same word, it is the same letter, but you should understand that this angle K is going to be the same when included in both the triangles. So I have one common angle and two angles are equal to each other, and therefore these two triangles are similar by the AA test. And now I can write the ratio of the sides. So I can say PN divided by LM is equal to NK divided by MK, which is equal to PK divided by LK, and this is because of corresponding sides of similar triangles. And now let's substitute the sides that we know. Do we know Pn? Pn measures x. So why don't we write all the measures here? Pn measures x, Nk measures c, then Lm measures a, and Mk. So Mk is the length of this whole side. So the length of Mk is going to be b plus c. So Mk is therefore equal to b plus c. So now I can simply substitute the values. Pn is x and Lm is a is equal to Nk. Nk is c and Mk is b plus c. And these two measurements are not given. So let us just drop them from the equation. And therefore, x is in division. It goes to the other side for multiplication. Therefore, x equals AC upon b plus c. And this is what we had to prove. So I would simply say, hence proved. So the ideas used in this particular problem were again common angle, parallel lines, concluding that the lines are parallel. And also the A test of similarity was used, and the simple idea of CSST helped us conclude that x is equal to AC upon b plus c. So I will just pause for a couple of seconds and then move on to the next question. Moving on to the next question. This is the given figure. We have to prove that BP into PD. Let us color these sides. BP multiplied by PD is equal to EP, that's this length, multiplied by PC, right? So now let us see which triangles should we choose to prove this particular to prove this equation. One obvious choice is these two triangles, simply because the sides that are given in this equation, they belong to these two triangles. So I believe that these two triangles will definitely help us. So if I want to prove the similarity of these two triangles, I already have a 90 and 90, which is good. And of course, these are vertically opposite angles. So by A test, I can prove that they are similar, and then hopefully I should get this particular equation. So let's start. Let's say consider. So let's consider triangle VEP and triangle DPC for similarity. So now we know that angle BEP is equal to angle CDP is equal to 90 degree, because this is already given to us. And we also know that BPE is equal to angle CPD, because these are vertically opposite angles. And therefore, I can say that triangle BEP is similar to triangle C. So let's see, B corresponds to C then E corresponds to D, so CD and P by the AA test. And therefore, I can say that BE divided by CD is equal to EP divided by DP is equal to BP divided by CP. This is because of corresponding sides of similar triangles. And now I can take these two parts of the equation, right? I can take these two ratios and simply cross multiply. So on cross multiplication, I will get EP multiplied by CP equals BP multiplied by DP, and this is exactly what I had to prove. So I would say hence proved. So again, the AA test over here was useful, and CSST helped us prove the given equation. So let's pause again for a few seconds before moving on to the next question. Moving on to the next question. Let's consider this problem. It's given that ABCD is a parallelogram. T is any point on BC. We have to again prove that DF, so let's again shade the sides. DF multiplied by EF is equal to FB multiplied by FA. So again, it looks like we should be using triangles DAF and BEF for similarity. So if I consider these two triangles for similarity, let me see what all is equal in these two triangles. So first of all, I think the vertically opposite angles can be claimed as equal for sure. And secondly, because ABCD is a parallelogram, I know that the side AD is parallel to side BE. And because these two lines are parallel, BD can be considered as a transversal, which means this angle is going to be equal to this angle, alternate interior angles. And therefore, by AA test, I can prove that these two triangles are similar. So, let us now construct the proof. So first, what I'm going to do is, I'm going to show that these two angles are equal. So I will say ABCD is a parallelogram. ABCD is a parallelogram in which AD is parallel to BC. So this implies angle ADF is equal to angle EBF, right? Because of alternate interior angles, right? So let's mark this as first conclusion. And now we should consider the two triangles for similarity. So I would start with consider triangle AFD and triangle BEF for similarity. And now let us write the parts which are equal. So I know that angle ADF is equal to angle EBF because of from the first result. We have already written the justification there, so we need not repeat it again over here. And also angle AFD is equal to angle BFE. This is because of vertically opposite angles. Vertically opposite angles. And therefore, I can say that triangle AFD is similar to triangle. Now, F corresponds to F. F is the second letter. Here also F is the second letter. D corresponds to B. So, D corresponds to B. Let's note that down here. And of course, the third vertex has to be E. This is by the AA test. And therefore, I can say that AF divided by EF is equal to FD divided by FB. FD divided by FB, which is equal to AD divided by EB, and this is because of the corresponding sides of similar triangles. Now, if you pick two equal parts, so I need DF and EF. I notice that I have DF and EF right in these two ratios. So let me cross multiply. By cross multiplying, I get. So I will say by cross multiplying. I get AF into BF is equal to DF into EF. And this is exactly what I had to prove. So hence proved. So again, it was a question of what triangles you pick. I decided the triangles after I just shaded the sides that are required, and that gave me a good hint of what triangles I had to pick. And then parallel lines and vertically opposite angles, they help me prove the similarity part. Again, let me pause for a couple of seconds before I move on to the next question. Okay, moving on to the next question. So let's consider this question now. The figure is given. ABC is a triangle. CE is perpendicular to AB and AD is perpendicular to BC. We have to prove these four subparts. So let's prove them one by one. Let us first concentrate on the first subpart. So we have to prove that triangle AEF is similar to triangle CDF. So let's go ahead and draw these two triangles separately. So I have drawn these two triangles separately over here. I have marked the two parts which are equal. I have 90 and 90. And angle AFE is also equal to angle CFD, which means these two parts are also going to be equal to each other because these are vertically opposite angles, right? And therefore by AA test I can say that these two triangles are similar. So let us write these statements. Consider triangle AEF and triangle CDF for similarity. I know that in these two triangles, angle AEF is equal to angle CDF, which is equal to 90 degree because this is given to me. and also angle AFE is equal to angle CFD because these are vertically opposite angles, right? These are vertically opposite angles, and therefore I can say that triangle AEF is similar to triangle CDF because of the AA test, right? So again, F corresponds to F, so F is the third letter here and here. E is 90, D is 90, so E corresponds to D. Both are equal to 90, and A is going to correspond to C. So by AA test, these two triangles are similar. Let me pause for a few seconds before we move on to the next pair. Moving on to the next subpart. So now we have to prove that triangle ABD is similar to triangle CBE. I have drawn these two triangle pairs separately, right? You will notice that every time I draw the figure, I keep the orientation exactly the same. So let us now consider which parts are equal. In these two triangles, angle D and angle E are both 90, so they are equal to each other. Similarly, angle B is equal in both the triangles. So again, by AA test, these two triangles are going to be similar to each other. So the concept used here was the concept of common angle. Again, not because the letter is same, but because the measure of angle B is same in both the triangles, right? So I would say consider triangle ABD and triangle CBE for similarity. So I can say that angle ADB is equal to angle CEB, that equals 90 degrees, and it is because this is given to me in the question. Also, angle ABD is equal to angle CBE because this is the common angle. And therefore I can say that triangle ABD is similar to triangle CBE because of the AA test of similarity, right? And hence proved. This is what we had to prove in this question. Pausing for a few seconds before we move on to our next question. Let's now try the third subpart. So now in the third subpart, we have to prove that triangle AEF is similar to triangle ADB. Let us now consider these two triangles. I have drawn these two triangles from the main diagram. I have kept the orientation exactly the same. So in these two triangles, I notice that angle E and angle D are both 90 degree. That's given to me. And angle A is now the common angle. So again, by AA test of similarity, I can show that these two triangles are similar. So I will say consider triangle AEF and triangle ADB for similarity. So now I know that angle FAE is equal to angle BAD because this is the common angle. Yeah, angle that is common. Angle that is common. That's basically the angle A, right? And also angle AEF is equal to angle BDA, because both these angles are equal to 90 degree, and that's given to me in the question. Therefore, I can say that triangle AEF is similar to triangle. A corresponds to A. E is 90 degree, so E corresponds to D, and then the third vertex is B. This is by the AA test, and hence proved. So again, pausing for a few seconds before I move on to my next question. Moving on to the next question. So in this fourth subpart, I have to prove that triangle FDC is similar to triangle BEC. I have drawn these two triangles separately here. You will notice that both these angles have a 90 degree, which is already given in the question. So I can mark the 90 degrees equal to each other. And also angle C happens to be the common angle in both the triangles. So how do I know that? Because if you notice in both the triangles, it is this part of C, angle C, which is getting counted, right? In both the triangles. That is why it forms the common angle. So what I can say is, I can say consider triangle FDC and triangle BEC for similarity, and therefore I can say that angle FCD is similar to angle FCD is equal to, not similar to, angle FCD is equal to angle, so C is being counted in this triangle, that corresponds to C here, so it is BCE, because this is the common angle, right? Common angle. And also angle FDC is equal to angle BEC, which is equal to 90 degree, and that's given to me in the question. Therefore, I can say triangle FDC is similar to triangle. Now, D corresponds to E, so D is the second letter, E is the second letter. C is the last letter, so is the C, so C is the last letter here also. So this is triangle BEC using the AA test of similarity, and this is what we exactly have to prove. Therefore, this is hence proved. So again, let me pause for a few seconds before I move on to the next question. One technique that I found very handy in all these questions was always draw the two triangles separately. If you can't visualize it very well, always draw them separately so that you can understand what parts are equal and what tests can be used for similarity. So pausing for a few seconds now. Moving on to the next question. Let's consider the following question. P and Q are points on sides AB and AC respectively of triangle ABC. The measurements are AP is 3 centimeters. So why don't we just note down the measurements. AP is 3 centimeters. PB is 6 centimeters. AQ is 5 centimeters. And QC is 10 centimeters. Prove that BC is thrice of PQ. So if I were to think of this problem, BC and PQ, these two sides are the corresponding sides, but not unless I prove that the triangles are similar. So the obvious choice for triangles over here to be similar would be APQ and ABC. Let me quickly draw them separately. So I have drawn these two triangles separately here. I have also marked the sides. AP was 3 centimeters as given in the question. AQ was 5 centimeters as again given in the question. AB, so AB will be 3 plus 6, that's going to be 9 centimeters. And similarly AC, the length AC here is going to be 5 plus 10, that's 15 centimeters. So I don't know whether the lines PQ and BC are parallel or not. I don't know if those line segments are parallel. But what I definitely see here is, if I take the ratio of the sides, so let's consider triangles. Consider triangle APQ and triangle ABC for similarity. I can say that AP divided by AB is 3 upon 9, that's 1 by 3. And similarly, the ratio of AQ and AC is 5 by 15, which is also 1 by 3. Now I notice that AP by AB is equal to AQ by AC, which is equal to 1 by 3. And also angle PAQ is equal to angle BAC, because this is the common angle. If you notice, in both the triangles, it is this particular angle that is being considered, and these two angles are equal to each other, so that's why that is the common angle. So now I have two sides which are in the same proportion. If you consider these two triangles, the ratio of PQ to BC is the same as ratio of AQ to AC, and the included angle is equal, right? This particular included angle is equal, which means that I can definitely use the Sas test of similarity here. So I can say that therefore triangle APQ is similar to triangle ABC by the Sas test of similarity. And because it is similar by the Sas test, I can also conclude that AP divided by AB is equal to PQ divided by BC, which is equal to AQ divided by AC. This is by corresponding sides of similar triangles. Now let us substitute the measures that we know. I know that AP is 3 centimeters and AB is 9 centimeters, which means I can say 3 upon 9 simplifies to 1 by 3. So 1 by 3 equals PQ by BC, which implies on cross multiplication BC is equal to 3 times PQ, hence proved. This is exactly what I wanted to prove, and this is how I used similarity. Over here the Sas test was used, so this is a good problem to check for the Sas test, and the angle was common, which is why using corresponding sides of similar triangles I was able to prove BC equals thrice of PQ. So let me pause for a minute before I consider the next question. Moving on to the next question. So let's consider the following question. It's given that QT upon PR is equal to QR upon QS and angle 1 and angle 2 are equal to each other. So because angle 1 and angle 2 are equal to each other, it tells me that triangle PQR is an isosceles triangle in which PQ and PR are both going to be equal to each other, right? So that is something that is there on the back of my mind. I have to prove that triangle PQS is similar to triangle TQR. So again, let me go ahead and draw these two triangles separately, and then we will figure out what all is equal. So I have drawn these two triangles separately. I instantly notice that angle Q is the common angle in both the triangles, because angle 1 is the angle that is getting counted in both the triangles. Now I have to show that these two triangles are similar to each other. So let's see the second part of the given statement. So it's given that QT divided by PR is equal to QR divided by QS. So why don't we go ahead and just mark the sides. QT, let me mark QT here. So QT divided by the corresponding part is PR. Now PR is not even there in any of these two triangles. But what I noticed earlier was PQ and PR have to be equal to each other because angle 1 and angle 2 are equal. So I can say that this is given to me. So since angle 1 equals angle 2, I can say that PQ equals PR by the isosceles triangle property. And therefore, in place of PR, I can substitute it with PQ. So I can rewrite this given statement as QT divided by PR can be replaced by PQ is equal to QR divided by QS. So now let us mark the parts which are equal, or rather which are in proportion. So QT divided by PQ, let me mark that side. QT divided by PQ is equal to QR. So let's mark QR. QR divided by QS, right? QR divided by QS. Do you notice that I can definitely use the SAS test of similarity? Two sides are in proportion. I have marked them with the same color and the included angle is equal, and therefore I can use the SAS test for similarity. So I can say consider triangle PQS and triangle TQR for similarity. So I can say that angle PQS is equal to angle TQR because that's the common angle, right? And also QT divided by PQ is equal to QR divided by QS. This is from 1. And therefore I can say that by SAS test of similarity, I can conclude that triangle PQS is going to be similar to triangle Q. In this triangle, Q in PQS corresponds to Q in TQR. So Q is the second vertex. PQ, so P corresponds to T and I have R, so TQR by the SAS test of similarity. So this is how we can prove that the two triangles are similar, and I will pause for a few seconds before I move on to the next question. Please take a look at the procedure. I will quickly summarize this again. We saw that I had an isosceles triangle. We saw that the two angles are equal. So I said that PQ should be equal to PR. I replace this PR by PQ over here, right? That is what I've done here. Then I drew the two triangles separately and then I marked the sides which are in proportion, and I also noticed that angle Q was common, so I was able to use the SAS test. So again, pausing for a minute before I move on. Moving on to the next question. So let us consider this question now. In this particular figure, it is given that DC is perpendicular to AC, then AB is perpendicular to AC, and OL is also perpendicular to AC. So basically we have a line segment AC and three perpendiculars are drawn to it. So DC is perpendicular to AC, OL is also perpendicular to AC, and BA is also perpendicular to AC. The measurements are as shown over here. So we have B, we have H, we have A, and then we have X and Y. We have to prove that H equals AB upon A plus B. In short, we have to eliminate X and Y from the equality. Somehow we have to get rid of X and Y. Of course, X and Y will be present, but eventually we have to get rid of them. So let's see how to go about this particular question. So first let me mark the perpendicularity. It's given that these angles are going to be 90. I know that. So these angles are equal to 90. Now some triangles should be useful. If I want H and B, okay, a relation between H and B, I should go with triangle AOL and ADC. So why don't we draw it separately and derive a relation? So if you take these two triangles, I notice that angle C is equal to angle L, and angle A is common in both the triangles. So I can definitely prove that these two triangles are similar. Let me do that over here. So consider triangle ACD and triangle ALO for similarity. I can say that angle DCA is equal to angle OLA, that equals 90 degree. This is given to me in the question. And also angle DAC is equal to angle OAL, and that is the common angle. And therefore I can say that triangle DCA is similar to triangle OLA by the AA test. So now using the concept of CSST, I will write DC divided by OL is equal to CA divided by LA is equal to DA divided by OA. So let us mark sides that I know. DC is B divided by OL is H is equal to CA is X plus Y divided by LA is Y. And I don't need the sides D and OA, so let me just ignore them. So let me mark this as the first relation. Rather, I will make a note of it over here in the box over here. So let's note down what relation we got. We got B upon H, or I can even take the reciprocal here. So I will get H upon B. The reason why I took the reciprocal was I noticed that H is in the numerator in the proof part. So because H is in the numerator, I would want H in the numerator here. So H upon B is equal to Y upon X plus Y. This is the first conclusion that I have reached. Let me pause for a couple of seconds so that you can grasp this, and then I will continue. Okay, let's move on. Now I need to find the relation between H and A. I have already found the relation between H and B. Let me find the relation between H and A. To find the relation between H and A, I think I will have to take triangle COL and CBA. So let me take these two triangles. Let me draw them separately, and then we will see how it helps us. So when I draw these two triangles separately, I have taken COL and CBA. Let us mark its sides. So we know that this is H and AB is A. Then CL is X and CA is X plus Y. Now these two triangles are definitely similar because angle L is 90 and angle A is also 90. And angle C forms the common angle in both the triangles, right? So these two angles are 90 and then I have a common angle in both the triangles. Let's mark the common angle. Therefore, by AA test, these two triangles are similar. So I will say consider triangle COL and triangle CBA for similarity. So now we have angle OCL is equal to angle BCA because these are the common angles. And similarly, angle CLO is equal to angle CAB because these two are equal to 90 degrees. This is given to me in the question. And therefore, triangle COL is going to be similar to, so C corresponds to C, O corresponds to B, and A by the AA test of similarity, which means CO divided by CB is equal to OL divided by BA, which is equal to CL divided by CA. This is by CSST. Now let's replace what parts we know. We know that okay, CO and CB don't matter over here. OL, how much is OL? OL is H. So H divided by how much is BA? BA is A is equal to how much is CL? CL is X divided by X plus Y. So therefore, now I have the second relation, which is H upon A is equal to X divided by X plus Y. Again, this is because of CSST. I will again pause for a few seconds before we move on to the final part of the solution. So in short, I have been successful in getting H upon A and H upon B in terms of X and Y. The only thing that I now have to think about is how can I get rid of x and y. That is the only thing that is left to be done. Otherwise, we are done with this solution. So again, pausing for a few seconds for you to take a look at the second part of the similarity. Okay, now let's take a careful look at both the equations that we have so far. So we have h upon b and h upon a. So h upon b is equal to y upon x plus y, and h upon a is equal to x upon x plus y. Somehow I have to get rid of x and y. I notice that if I add these two equations, something is going to happen to the right hand side. So if I do h upon b plus h upon a, what is the denominator? The denominator is x plus y. So the denominator is x plus y. And the numerator will become y plus x. So when I add these two, this is equivalent to adding two fractions. So y upon x plus y plus x upon x plus y. And the denominator is same. That is why I can simply add the numerators. So I get y plus x upon x plus y, which simplifies to 1. And therefore, h upon b plus h upon a is equal to 1. The great part about this is x and y are eliminated now. Now I can take the LCM. The LCM of this is a into b. H gets multiplied by a, so this is HA, and b gets multiplied by h, so this is HP equals 1, which means HA plus HB is equal to a multiplied by b, shifting the AB to the right hand side for multiplication. Taking h out as common from this, I get h bracket a plus b is equal to a multiplied by b, which means h is equal to ab divided by a plus b. And this is the equation for the height h in terms of a and b. And this is what we had to prove, hence proved. So again, let me repeat. I had h upon b and h upon a. I added these two because I saw that the denominators are x plus y in both cases. So when I added, I got y upon x plus y plus x upon x plus y. LCM is x plus y and the numerator was y plus x. This cancelled and I got a 1 here, right? So h upon b plus h upon a was equal to 1. On taking the LCM was AB. So HA plus HB is equal to AB. AB was transposed to the other side for multiplication. So HA plus HB upon AB equals 1 resulted in HA plus HB is equal to AB. In these two terms, I took H out as common. So H bracket A plus B was AB and H is therefore equal to AB by A plus B. So this is how I proved this particular problem, and let me now pause for a minute and we conclude today's session over here. Okay, concluding today's session.